We now live in an exciting age where computation is becoming more and more accessible to young children. And yet, classrooms today, by and large, remain the same. How can computation become a part of public school classrooms? This is the research question we are trying to answer.
So, over the past 4 years, we have been developing a programming language called VMAP. And it's really a programming language and a modeling platform combined. Unlike traditional programming languages, VMAP is distinct in its origin, in that from the very beginning, our goal was to design a programming language that actually works in the traditional, regular classroom with teachers who we have currently. VMAP uses the powerful NetLogo platform as its simulation engine. This allows VMAP to represent really complex phenomena using NetLogo simulations and make them accessible and programmable for young learners using intuitive visual programming commands. There are 3 classes of VMAP languages: VMAP Sims, VMAP Image Computation, and VMAP Tangible. VMAP Sims allows the learner to build computer simulations of any phenomenon. VMAP Image Computation allows the learner to engage with the computer using a different modality. It literally allows the learner to bring their doodles to life. VMAP Tangible allows the learner to connect VMAP Sims and VMAP Image Computation with the sensors that are outside the computer using an Arduino microcontroller.
With science, like the concepts, I mean, a lot of times in the past in a traditional teaching, which, I don't really do well, dealt with a concept in science and a concept in math and a concept in reading, and those were kind of separate blocks. VMAP has kind of allowed the integration of those 2 curriculums, or even 3 curriculums.
So we were able to incorporate the different subjects. We incorporated science, we incorporated mathematics into a very science-heavy activity, but where we were working on multiples, multiples of 3, multiples of 5, multiples of 7, different things like that. We were able to incorporate that into the computer software, and for them to see it not only like mathematically, but also visually with the charts and the way that the turtle would move and just different things and make the different colors. And that way I could take what we were doing there and use it in the classroom later on. They were also able to use their creativity, just innovate, ideas, especially like my lower kids that I wouldn't have expected to really have just bringing out these ideas. It was just the journey from the beginning of the year to the end of the year.
What we have learned fundamentally is that for the successful integration of computation as the language of science in a science classroom, we must have a long-term focus as opposed to short-term interventionist studies. Our research methodology is longitudinal and design-based. We conduct year-long and multi-year-long studies on integrating computational thinking and modeling with upper elementary and middle school science. Our studies investigate how teachers and students appropriate and develop programming as the language of science through multiple iterative cycles of modeling. When teachers and students encounter VMAP for the first time, they're always encountering VMAP in the context of a science topic. So for example, for the first time that a 3rd or a 4th grade teacher encounters VMAP, it's typically going to be in the context of teaching, say, like kinematics or force and motion. So the version of VMAP they get has programming commands that are meaningful also in terms of the physics involved. So the learners have to specify the step size of each turtle. Then there are graphs that the learners can also design and generate, and these graphs tell them how far the turtle has moved and the speed and the acceleration and so on and so forth. Activities in classrooms don't just involve books and symbols. They also involve students and teachers dealing with and using found objects, and sometimes very specific objects like rulers and calculators. For computation to become a part of that world, it really needs to be integrated. That is, the computational practices need to be meaningfully integrated with the material forms that are accessible to teachers and students in the classroom.
Their activity becomes very entangled in the material nature of their work, and that creates lots of problems for them. Students would say things like, I know our measurements are a little off because the flags stuck to so-and-so's shoes. But the more students face these resistances and accommodate those resistances with the material world, it creates new opportunities to learn.
Teachers must find a voice as computation is being used in their classrooms. What we have found is that when teachers appropriate programming, they typically reframe programming in the context of teaching and learning science as a form of mathematizing the world around the students.
So you had your inquiry-based experiment with science. You had your mathematics, where you took your formula for speed, and then you had your VMAP that brought the two together. So it was a real experience that students can relate to. They're involved, they're up moving around, they have the math, they have the science, and they can integrate that into a whole concept and really understand like what speed and distance is.
Well, I think VMAP is designed to work with teachers and with the curriculum, national curriculum. So what they're doing day to day, VMAP doesn't sideline that, it actually works with that. And what we have found in the research that we've done with teachers is that rather than teaching programming, teachers really fall back on the practices that they know, so teaching science and mathematics. And what comes out in using VMAP is that in addition to helping to develop model-based reasoning in science, what we have found is that students are also developing socio-mathematical norms.
So, what happens when programming does become the language of science? Over the past 4 years, our research has shown that first, VMAP can make very complex phenomena accessible to students as young as 3rd graders. And second, when teachers are readily in charge of the curriculum, the students show very high gains over long term in math, science, and reading test scores, in addition to developing new fluencies like programming and modeling. And third, we've found that by showing how different domains can be brought together, this research also suggests that computation in the classroom can bring a wide variety of academic subjects together that were separate in the traditional classroom. Perhaps this is what computation-enabled classrooms will look like in the near future.